Alright, so today we're going to talk about this thing called Hess's law. And as we're talking about thermochemistry, it turns out that Hess's law is used for adding equations together, reactions if you will. So what does this actually mean? Well, if we had two reactions, let's say it was a solid goes to B gas, and we'd said something like, well, this has a delta H of positive 5. And then I had a second equation that looked something like this. Well, a solid goes to C, also gas. I told you that this delta H here was 36. What I can do is I can actually add these two equations together and I get something that looks like this. 2A solid goes to B gas plus C gas. The delta H here then is the sum of their two delta H's. Now this has interesting implications when you have things that cancel. So you can see that the two A's actually stacked on top of each other. But you can imagine then that if I had, say, the second equation flipped, kind of like reverse, then the actual equations would cancel. And so Hess's law allows us to play with this equation a little bit and combine them together in new and novel ways. Well, what do I mean by that? Well, let's just pretend that I erased all of this and went back to the second equation. But instead of adding these two equations together, I decided that I was going to rotate this equation left to right. What does that mean? It means that what I'm going to do is just swap them from left to right. So now I have C. So all I did was I switched it. Does that change my delta H in any meaningful way when I take an equation and I swap it left to right? Kind of. If I had an equation that looked like this, now I have an equation that looks like this. Essentially I've taken this and I've turned it from left to right. Does that change the numerical difference between them? No. What does it change? Kind of the orientation, but what it really changes is this one goes down. This one's exothermic, and then this one on the right here is endothermic. What do we know about the delta H between exothermic and endothermic? One's positive and one's negative. And so what it does is it flips the sign. So instead of 36, which I had before, it's now negative 36. But what happens when I actually add these two equations together? Well, this is what happens. You get something that looks like this. A solid plus C gas. And then on the other side, I have A solid plus B gas. And here's where it gets really interesting. It turns out that these two, the A's, are on opposite sides, and like a spectator, they will cancel. So what are we left with then? Well, if I remove these, just kind of delete them, what I'm left with is just B goes to C. When B goes to C, the delta H here is 5 plus negative 36. So Hess's law allows me to play around with the equations that I have delta H's for, and combine them in new and novel ways to try to then find an equation, and it's delta H, to something that maybe I cannot perform. Maybe it's a reaction that doesn't actually occur. Or this is a multi-step reaction where I have a starting reactant and an ending product that has multiple steps along the way that I don't really care about, but I can cancel out by using some fancy changes to this additional thing. Now this works across multiple equations. It doesn't have to be just two equations that you're adding. You can add as many equations together as you want, the delta H just simply stacks up. So this brings us to a couple of different rules. The first rule is that reactions that generally release energy are exothermic, and the reactions that absorb energy are endothermic. The delta H tells me whether it's exo or endo by its sign. So we typically see reactions that look like this, reactions that look like this. So these two pictures show a reaction that is exothermic versus endothermic. But it turns out that if we take a reaction and we just flip it from left to right, we just swap the reactants and products, the same thing happens. We just get this exact same picture, but it gets kind of like inversed. The inverse has the same difference in height. The height difference between the starting and the ending is the same. The only difference between them is the sign of that difference. In this case, we have a negative delta H. Now, in this case, we have a positive delta H. But numerically, they should be the same. It's the same difference between their energy values. So because the sign changes when we flip the reaction, what we can do is capture this in a series of rules that we can use. So the first kind of permutation is we can change an original reaction by doing a couple of things to this. So I'll call these alterations to the original equation a kind of permutation. So you can take the original and then you can kind of mod it a little bit. Okay? There's two types of mods that are allowed. The first type of mod is called a multiplier mod. And the way a multiplier mod is you apply some multiplication to it. Okay? So you can do like a times 2. That would be okay. Or you can even apply a divided by 2. Or any other numbers. You can think of the divided by 2 as simply multiplying by half. You're going to do half of an equation. Okay? But what happens to the delta H when you only run half the equation, or if you run double the equation? Well, if you upgraded from an iPhone 6 to an iPhone 8, and the difference is $200, what happens if you do 2 iPhone 6s and you upgrade to 2 iPhone 8s? You would then need to throw in how much money? $400. It's exactly double. And so what happens is, when you do a multiplier, the delta H value is also multiplied by the same multiplier. Okay? So if you can upgrade half of an iPhone 6 to half of an iPhone 8, that'd be kind of cool. You would only have to throw in $100 because you're only doing half of the reaction. Okay, that sounds kind of impossible, Mr. Chen. But remember, we're dealing with moles, right? So you can definitely have half of a mole, because a mole is actually 6.02 times 10 to the 23rd particles. You can definitely do half of a mole fairly easily. The second kind of mod is to do what I call a flip. You basically take an equation and you just flip it from left to right, and you basically do the reverse of the reaction. And in this case, the delta H just changes sign, meaning that if it were positive, it would then become negative. If it were negative, then it would become positive. And the reason for this is because it switches from an exothermic to an endothermic reaction when we do this kind of swap. All right, so let's do a sample reaction. Here's our goal. Our goal at the end of the day is to find the delta H for this reaction. Hess's law allows us to find the delta H for this reaction if we had some other types of information. Okay? And the way they're going to give us this information is they will give us some reactions that kind of have to do with this main reaction. So these are called component reactions, and the component reactions look roughly like this. S solid plus oxygen gas makes SO2 gas, and it has a delta H of negative 297. What's most interesting, of course, is that the SO2 is not in that target reaction. The SO2 is actually not something that shows up in our goal. But the S and O2 do, and so this gives us a hint as to what we need to do. Let's take a look. Here's the second component reaction. 2SO3 goes to 2SO2 plus O2 gas with a delta H of positive 198 kilojoules. So at this point, what I'm going to do is I'm going to kind of get my highlighter out just to kind of show you how to think about these type of reactions. And I'm going to try to show you where the pieces are coming from. So if I'm looking for this S, do you see the S located anywhere in the component reactions? Is it located in A or B? Do you see the S located anywhere? It's located in A. I'm going to switch colors here, and let's talk about this O2. Do we see O2 in any component reaction? It's located in both A and B. And I'm going to switch colors again. Let's go ahead and use green. Do we see SO3 anywhere? It's located in B. So the way this is going to work is I'm going to try to get the components that are unique. The unique components are the S in yellow and the SO3 in green, because they only show up in one of the component reactions. And what I'm going to do is I'm going to try to get them to match up, meaning that they have the same multiplier and they're on the same side of the equation. Okay? And so what I'm going to do is I'm going to look for unique ones, and try to get same multiplier and same side. Okay? So for now, I'm going to kind of ignore the orange. The orange is located in two reactions, and so I'm going to kind of hold off on that one. So I'm going to go ahead and erase that so we can see that we're working with the yellow and green at this point. Okay, so let's analyze this first one, this yellow one. Is it on the same side of the equation? The target's on the left. Is it on the left in component A? Yes. Okay, so it's on the same side of the equation. We don't have to touch that. But do they have the same multiplier? No. And so what I'm going to do is I'm going to change the multiplier of this one here, and I'm essentially going to double everything in A. So it's going to be 2, 2, and 2. I'm going to take all the coefficients and multiply by 2. And the delta H then also gets multiplied by 2. Essentially, I'm going to run it double. At this point, I have the 2s that has the same multiplier, and it's on the same side of the equation as my target. I'm kind of done with this one here. Okay, I'm going to move on to the green. Looking at the green, are they on this? Is it on the same side of the equation, this SO3? No. So what I'm going to do is I'm going to flip this equation from left to right. I'm just going to do just a flip. And the way I'm going to write this is I'm going to write it underneath it, and I will call this B2. And all I'm going to do is I'm physically going to flip it from left to right. So no changes to the actual equation itself. But what happens to the delta H? It becomes negative when we flip things. So, same equation, I've just literally flipped it from left to right. And now let's check. Is the SO3 on the same side of the equation? Yes? Does it have the same multiplier? Yes. Okay. So what I'm going to do at this point is I'm going to add the two equations together. Okay, so which two equations am I going to add together? Well, I'm going to add this first one that I've modified with B2. These are the two I'm going to add together. Alright? And the way I'm going to add them together is if they are exactly the same, they will then stack up. If they cancel, meaning that they are the same thing on both sides of the equation, then I can essentially cross them off. So let me show you how this works. So I'm going to take everything on the left side and add it to everything on the left side here. Essentially, we're going to stack it all the way down. Okay? You ready? Here we go. I have 2s plus 2O2 I also have 2SO2 plus another O2. And on the other side, I'm going to add up everything else. 2SO2 plus 2SO3. Okay, so I've just gathered everything on the left together and everything on the right together. Now, this is quite a mess, but I'd like you to look for things that you can stack together, meaning that they're the same and you can gather like terms, or if there's something that you can actually cancel out, like a spectator. Okay, let's check in. Is there anything I can cancel out? Okay, so the 2SO2 is located on the left side as well as the right side, and they're exactly the same. Same coefficient, so they will cancel out. They're like spectators. Let me get my eraser and just pop it off. Beautiful. Okay, and is there anything else I can do to kind of simplify this? The 2O2 and O2 can be stacked together, and when we stack them together, what happens? Okay, so we get 3O2 instead. Okay, so go ahead and clean that up a little bit. What do you see over here that's left behind? Does it match our target equation at the very beginning? Yes, very good. But this doesn't really solve what the question is asking me to do. What is the question asking me to do? Find the delta H. To find the delta H, I need to add the two delta H's together. And these are the two that I added together. And so to find the delta H, I actually need to basically do negative 297 times 2 and add this to negative 198. When I do this, it should then give me the delta H. Go ahead and compute that, and we'll check in a minute to see how you did. Okay, I have a negative of delta H of negative 792 kilojoules. Cool.